Okay, good afternoon students. Yesterday we have completed one problem in isothermal process or constant temperature process. Today we will take some more problems in isothermal and some problems in a hyperbolic process. So we will go to the second problem. So 1 kg of steam at a pressure of 7 bar and 0.95 dry is expanded isothermally to a pressure of 1.5 bar with a temperature of 165 degrees C. Find change in enthalpy, change in internal energy, change in entropy and heat transfer when Cp is equal to. Second problem, 1 kg of steam at a pressure of 7 bar and 0.95 dry is expanded isothermally to a pressure of 1.5 bar with a temperature of 165 degrees C. Find change in enthalpy, change in internal energy, change in entropy and heat transfer by taking Cp is equal to 2.1 kilojoules per kg Kelvin. So here you observe the initial condition of steam is 7 bar and 0.95 dry. That means the initial condition is actually wet steam. See, observe here. So the initial condition of steam is wet because 7 bar and 0.95 dry, the dryness fraction is given. Next is expanded isothermally. The process is isothermal to a pressure of 1.5 bar. Initial pressure is 7 bar and final pressure is 1.5 bar with a temperature of 165 degrees C. So this is also important. So easily you can decide the final condition of steam is superheated. So initially it is wet and finally it is superheated. Okay. Now you should find the 4 parameters, that is change in enthalpy, change in internal energy, change in entropy as well as a heat transfer for isothermal process. So I have taken the values for initial pressure of 7 bar and final pressure of 1.5 bar. I have taken all the values from the steam table, Vg, Hf, Hfg, Sf and Sfg. These two values why I have taken, because we want change in entropy also. Next first we will find one by one. First, change in enthalpy, that is what? Delta H. So delta H is equal to, I have taken H sub 2 minus H wet 1. Why? Because the final condition is superheated and initial condition is wet. So first find enthalpy of steam at the initial, that is H wet 1. You know the formula, Hf1 plus x1 Hfg1. So x1 is given, that is 0.95 and Hfg and Hf1 we have taken from the steam table. We have enthalpy of wet steam is around 2658.75. Similarly, enthalpy of steam at final. So final condition is temperature is given, therefore it is superheated. So therefore enthalpy of superheated formula you know. So substituting all the values, so you will get around H sub 2 is 2805.96 kilojoules per kg. Therefore change in enthalpy, delta H is equal to the final enthalpy minus initial enthalpy, that is 2805.96 minus 2658.75 will give around 147.21 kilojoules per kg here. So initially is wet, finally it is superheated, therefore the enthalpy is positive because this much of heat is added to the steam, so it becomes a superheated steam, right. Second thing, we want change in internal energy. Change in internal energy is nothing but delta E, that is equal to final internal energy minus initial internal energy. So first we will find initial internal energy. Initial condition of steam is wet, so that is E wet I have taken here. Say E wet is equal to H wet minus 10 square P1 x1 Vg1. No need of substituting formula again for H wet 1 because we have H wet value here, that is 2658. Directly you can substitute. So 2658 minus 10 square P1 x1 Vg1 will give around 2477.2 kilojoules per kg of internal energy for initial condition of steam. Now what is the final condition of steam? That is superheated, because temperature is given, Therefore, I have taken E sub 2 formula. So, that is HF2 plus HFG plus Cp T sub minus T sat minus this is the work done for superheated steam, that is 10 square P2 V sub 2. For V sub 2 directly you can substitute the formula here, or you can find V sub 2 separately like this. Say V sub 2 is separately calculated by using the formula Vg2 T sub plus 273 divided by T sat plus 273. So, substitute all the values. So, we will get V sub 2 is around 1.32 meter cube per kg. Therefore, E sub 2 is 2607.96 kilojoules per kg. Therefore, change in internal energy delta E is equal to final internal energy minus initial internal energy. Final is superheated, initial is wet. Therefore, E sub 2 minus E wet 1 is give around the delta E is around 130.76. Here also the answer is positive. Why? Because the wet steam initially it is wet, after the process it is superheated. Therefore, the answer is positive, that is heat is added to the steam. Next, third is change of entropy. So, initial condition of steam is wet steam. Therefore, I have taken S wet 1 is equal to SF1 plus X SFG1. So, we have both the values from the steam table, X is given in the problem. So, S wet 1, that is entropy at initial condition is 6.469 kilojoules per kg Kelvin is the entropy of initial steam. Next, final superheated, you know the formula for entropy of superheated steam, SF2 plus SFG2 plus 2.3 Cp log T sub plus 273 divided by T sat plus 273. So, substitute all the values one by one. So, you will get S sub 2, that is entropy of steam after the process is 7.496 kilojoules per kg. Therefore, the change in entropy delta S is S sub 2 minus S wet 1. Final entropy minus initial entropy is around 1.027 kilojoules per kg Kelvin. So, this is the change in entropy. Finally, for isothermal process we want heat transfer. Yesterday already we have completed one problem. So, Q is equal to T sub plus 273, because you should take in Kelvin, into change in entropy. Change in entropy is 1.027 from the previous equation, and T sub is given in the problem. So, you will get 450.17 kilojoules per kg of heat is added to the steam. So, like that in isothermal process you should calculate all this, that is change in entropy, enthalpy, heat transfer, and final condition of steam also you can calculate it in isothermal process. Okay. Next, we will go to hyperbolic process. This is an important process. Hyperbolic process means PV is equal to constant. That means a product of pressure and volume before and after the process remains the same. That is called hyperbolic process. So, the first problem on hyperbolic process, steam at a pressure of 10 bar and 0.9 dry. So, first you should identify the initial condition of steam. 10 bar and 0.9 dry means it is a wet steam, expands to atmospheric pressure. See, this is important. So, there is a underline here, atmospheric pressure, that is the final pressure is atmospheric pressure. So, atmospheric pressure means the value of atmospheric pressure is 1 point, see here in the steam table here. So, 1.013 is the atmospheric pressure of steam. So, they are not giving the values, just they will give like this 2 atmosphere or 2 atmospheric pressure. In that case, you should take the value of pressure is 1.013 bar. Okay, next hyperbolically, the process is given hyperbolic. Find 4 parameters you should find: work done, change in enthalpy, change in internal energy, and heat absorbed. So, Cp is given 2 kilojoules per kg Kelvin. So, initially 10 bar 0.9 dry wet steam expands to atmospheric pressure hyperbolically. The final condition of steam is not known, only the pressure is known. We should find all this, right. First we take the values from the steam table for initial pressure of 10 bar and atmospheric pressure, final pressure of 1.013 bar. All the values I have taken. Next we will find work done first, or you can find the final condition of steam also, anything you can find first. So, first you will find the work done. In a hyperbolic process, work done W is equal to 2.3 into 10 square P1 V1 log V2 by V1. See here V2 by V1 R is equal to P1 by P2. So, here I have taken P1 by P2. Why? Because P1 and P2 both are known values, both are given in the problem. See this is P1, this is P2. Therefore, I have taken P1 by P2. So, substituting the values, P1 is given, x1 is given, Vg1 is there from the steam table, and here P1 is 10 and P2 is 1.013 bar. So, you will get around 399.32 kilojoules per kg. Right. Next to change in enthalpy. So, change in enthalpy means delta H. So, to find delta H, we know initial condition. Initial condition is what? Wet steam, but final condition is not known. The pressure is known, say 1.03 or atmospheric pressure, but whether it is dry or superheated, we do not know. Therefore, first we should find the final condition of a steam or quality of steam by using a dryness fraction formula. That is, see here, x2 is equal to, this is a hyperbolic law, P1 V1 is equal to P2 V2. By expanding, we have P2 V2. See, P1 V1 Vg1 or P1 x1 Vg1 is equal to P2 x2 Vg2. In this relation, in a hyperbolic law, the final dryness fraction x2 becomes x1 P1 Vg1 divided by P2 Vg2. Substitute all the values, you have all the values, you will get x2 is, observe the value is 1.03 is the final condition of steam or dryness fraction of steam after the process is 1.03. It is more than 1. Therefore, the final condition of steam is superheated. Initially it is wet, now the final condition is superheated. For all final conditions, you must use superheated formulas only. Okay. First we will see, find V sup 2. V sup 2. Now the relation changed. Earlier we do not know the condition of the steam, therefore we assumed that initial and after the process the condition is wet. So, but after getting x2, it is more than 1.03, now it is decided that it is a superheated steam. Therefore, you must use a relation like this, P2 V sup 2 you should take, x2 Vg2 you should not take because it is superheated. So, by taking like this you should find the value of V sup 2, that is around 1.723 meter cube per kg. I already told you, when the steam final condition of steam becomes superheated, you must find T sup or degree of superheat, that is T sup minus T sat. So, that we got here, see here, T sup 2 is equal to T2 V sup 2 divided by Vg2 from this relation. So, you will get T sup 2 is equal to, substituting all the values. So, here you are getting T sup 2 is around 111.14 degree C is the superheated temperature of steam. If you want degree of superheat, so find T sup minus T sat is, say T sup is 111.14 and T sat is here 100 from the steam table. So, 111.14 minus 100, you will get around 11.14 degree C of superheat. So, now we have the superheated temperature is 111.14 degree C. Now, find the enthalpies. So, first enthalpy of steam initially it is wet, therefore, HF1 plus XHFG1 is the enthalpy of steam initially, we got around 2574.8. Next, after the process, after calculating the value of x2, we know that it is superheated, therefore, I have used enthalpy of superheated formula here. So, the formula is HF2 plus HFG2 plus Cp T sup minus T sat, substitute all the values. So, you will get around 2698.28. You observe the values here. Enthalpy initially is 2574, after the process it is more, that is 2698. That means initially it is a wet, after the process it becomes superheated steam, that means heat is added. So, the quality improved, therefore, we got a more value for H soup 2. Next, therefore, change in enthalpy, delta H is equal to final enthalpy minus initial enthalpy. Final it is superheated, initially it is a wet steam. So, that is 2698.28 minus 2574.8, you will get around 123.48 kilojoules per kg of enthalpy changed. Next, change in internal energy. In the derivation for a hyperbolic process, the change in internal energy delta E is nothing but delta H. In the conclusion, I told you, in a hyperbolic process always the change in internal energy is equal to change in enthalpy. Therefore, no need of substituting here E wet 1 or E soup 1 formulas, because in hyperbolic delta E is nothing but delta H. Therefore, I have given star here, star, that is important. So, we have a value of this delta H, you know, around 123.48, directly you can write here. So, therefore, change in energy always in a hyperbolic process is equal to change in enthalpy, that is also 123.48 kilojoules per kg. Now, heat transfer, according to first law, the amount of heat transfer Q is equal to change in internal energy plus work done. This is same for all the process. Now, therefore, heat transfer Q is equal to delta is 123.48 plus work done in the first equation you got around 399.32. So, totally we have 522.8 kilojoules per kg of heat is transferred to the steam. That is, initially it is wet, by transferring this much of heat it becomes a superheated steam. So, in hyperbolic this is very important, point number 3 is very important, because in hyperbolic delta E is nothing but delta H. Okay. So, we will go to the fourth problem, wet steam. So, initially he has given clearly wet steam at a pressure of 2 bar and 0.8 dry. So, 2 bar pressure is there, 0.8 dry means it is a wet steam. So, initial condition of steam is wet steam. Next, is compressed till its volume becomes, say this point is important, it is compressed till its volume becomes 1/4 of its original volume. That means, the final volume is equal to 1/5 of initial volume. Original means initial volume, that is V2 is equal to 1/5 of V1, right. If the compression follows, the law is also given, PV is equal to constant, that means hyperbolic law. The product of pressure and volume is equal to constant in a hyperbolic process. When hyperbolic process is there, immediately you should know that delta E is nothing but delta H, change in internal energy is equal to change in enthalpy. Next, find 3 parameters, final pressure of steam. So, observe the problem, no final pressure is given, right. Next, dryness fraction, both you should find. Number 2, change in internal energy, and number 3 actually heat flow, right. So, from the steam table I have taken value for only one pressure, that is initial pressure of 2 bar. So, for 2 bar T sat value, Vg, Hf and Hfg value I have taken, because final pressure is not known, but the one value is given, that is final volume is equal to 1/5 of initial volume, right. First we will find the final pressure. So, what is the law? Hyperbolic law. Hyperbolic law means P1 V1 is equal to P2 V2. Here P2 is equal to P1 V1 by V2 by cross multiplication, because I want final pressure P2. Therefore, so P1 is given, that is 2, and V1. So, V1 is V1, you take V1, say here you observe here in the problem, in the data he has given the final volume is V2 is 1/5 of initial volume. So, in place of V2 here, in place of V2 you substitute 1/5 of V1. So, that phi will go up because it is 1 by 5, denominator is 1 by 5. So, phi will go up and V1 gets cancelled, we left with P2 is equal to P1 into 5. So, P1 is how much? 2 bar and this is 5. So, 2 into 5 is 10 bar. So, final pressure of the steam is 10 bar. Like that you should find the final pressure of steam. Initially it is 2 and finally it is 10 bar. So, now I have taken the values for 10 bar, that is final pressure, all values I have taken. Next, dryness fraction. So, in this law P1 V1 is equal to P2 V2 because hyperbolic law. By substituting the values like this, see P2 x2 Vg2 is equal to P1 Vg1 x1, like that you substitute. So, you will get x2 value, that is final dryness fraction is 0.73. See, initial condition is also wet, final condition is also wet in this problem. So, initial condition is wet because he has given 0.8 dry, 80% dry steam is given. After getting final pressure, we got the dryness fraction is around 0.73. Initially it is 0.8, after the process it is 0.73. It is less than initial dryness fraction. That means, in this process some of the heat is rejected. The quality of the steam after the process is low compared to initial condition, right. So, 0.73. Now, it is very clear, initial condition and final condition, both the conditions are wet steam. Okay. Next, change in internal energy. So, in a hyperbolic process I had already told you delta E is nothing but delta H. No need of finding a delta E by putting a longer relations, you just find delta H. Say initial condition is wet, therefore, I have taken H wet 1, HF1 plus HFG1, you are getting 2266.22. Similarly, finally, it is also wet in this problem. So, the same relation we have used, but HF2 plus XHFG2, HF2 and HFD you take for 10 bar and X value we got is 0.73, the value is 2233.96. Therefore, delta H, delta E is nothing but delta H, finally it is H wet 2, initially it is H wet 1. So, we got minus. So, at the beginning I told you, because of lesser dryness fraction compared to initial condition, see here we got a minus answer. That means, the quality has reduced, that is minus 32.26 kilojoules per kg of internal energy changed or reduced. Next is work done. It is a hyperbolic law. In hyperbolic law, work done is equal to 2.3 into 100, that is directly I have taken 230 into P1 x1 Vg1 log P2 by P1 by P2. So, both P1 and P2 is given. So, directly I can take P1 and P2. So, 2 and 10 bar. So, substituting all the values I am getting again here see minus, because the same reason quality has reduced compared to initial condition. Therefore, work done is also minus around 227.89 kilojoules per kg. This is the work done. Next, therefore, heat transfer according to first law, Q is equal to delta E plus W. Delta E is what? Minus 32.26 plus W is also minus 227.89. So, minus 32.26 plus minus 227.89, together we have minus 260.15 kilojoules per kg of heat transfer. That means, here initially it is 0.8, after the process 0.73, both the conditions are wet, but the quality has reduced. Therefore, all the answers delta E, delta H, work done, heat transfer, all are negative, right. So, these are the problems on a hyperbolic process. So, next we will go to next process, that is a adiabatic process. It is also called as a reversible adiabatic process or isentropic or constant entropy process. So, this process is important for the next chapter. So, what is adiabatic process or isentropic process? In this process, the entropy remains same before and after the process. So, in adiabatic process the entropy means what? Transformation of heat. It is a function of temperature only. That means it increases with the addition of heat or it decreases with the reduction of heat. Okay. The entropy remains the same before and after the process. The entropy is denoted by what? S. Therefore, I have taken like this, S1, that is before the process, is equal to entropy after the process S2. Here there is no heat transfer. So, this point is very important. In all adiabatic processes there is no addition of heat or there is no rejection of heat. Therefore, there is no heat transfer, but work is done on the piston by expanding the steam because of expansion of the steam. So, because of expansion of the steam, what happens? Work done takes place on the piston, but no heat is added and no heat is rejected. Therefore, your entropy remains the same before and after the process, right. So, derivation. So, in all the process we have considered 1 kg of wet steam, assuming both the condition, that is before and after the condition, still the steam is in wet condition. So, we have taken wet steam being heated by reversible adiabatic process from initial state 1 to final state 2 in PV and TS diagram. Okay. So, P1 is initial pressure, P2 is final pressure, Vg1 initial specific volume and X1 is the initial dryness fraction. Similarly, P2, Vg2 and X2 are the corresponding values after the process. Okay. The initial volume of 1 kg of wet steam, that is V1 is equal to what? X1 Vg1, similar to all other processes. This is similar to all the process. Next, the final volume of 1 kg of wet steam V2 is equal to X2 Vg2. After that, according to adiabatic process, what is adiabatic process or adiabatic law? Entropy before the process is equal to entropy after the process. So, entropy before is what? S wet 1, because we have taken 1 kg of wet steam. Next, S wet 2, the final condition also we have assumed it is a wet steam. Therefore, S wet 1 is equal to S wet 2. There is entropy of wet steam. What is the entropy of wet steam relation? This one, SF1 plus X1. SFG1 is a entropy at initial. Next, after SF2 plus X2 SFG2, this is the entropy after the process. So, from this we have the final dryness fraction X2 is, see here the relation X2 is SF1 plus X1 SFG1. This SF2 becomes minus SF2 divided by cross multiplication, this will becomes here SFG2. This is the final dryness fraction of the steam in adiabatic process, right. So, here there is a note similar to other processes. If the final condition is dry, that means after finding X2, the value X2 is becomes 1 or exactly 1, then the final condition of steam is dry, then this relation becomes like this. So, here I have given SF1 plus X1 SFG1 is equal to SF2 plus SFG2. There is no X2 here because X2 is equal to 1. Suppose if X2 is more than 1, then the condition is superheated, then the same relation is changes like this, SF1 plus X1 SFG1 is equal to S sub 2, because the final condition is superheated, right. Next, change in internal energy, this we know delta E is equal to E2 minus E1. So, initially it is a wet steam, therefore, I have taken the initial internal energy of 1 kg of wet steam, that is E wet 1. E wet 1 is nothing but H wet 1 minus W wet 1, we know the formulas. So, H wet 1 minus 10 square P1 V1 is the initial internal energy of the steam. Next, final internal energy of 1 kg of wet steam, the same relation, that is E wet 2 is equal to H wet 2 minus W wet 2. For that, the formula is this, H wet 2 minus 10 square P2 V2. Therefore, delta E, that is change in internal energy, becomes E wet 2 minus E wet 1. So, this is the change in internal energy. This is similar to previous cases also. Next, heat transfer during the process. So, this area is important now in adiabatic process. According to the first law of thermodynamics, we know that heat transfer is equal to change in internal energy plus work done. This is the first law of thermodynamics. So, here in this process the heat transfer is 0 because entropy before and after the process is the same. Therefore, there is no heat addition or rejection, therefore, Q becomes 0. Therefore, what happens here? In place of Q, 0 is equal to delta E plus W. So, from this if you want delta E, if you want change in internal energy delta E, it becomes minus W, or if you want work done W, it becomes minus delta E. Why? Because Q is equal to 0. That means change in energy is nothing but minus W, or work done is nothing but minus change in internal energy in a adiabatic process. So, in the problem they will ask to find change in internal energy or work done. So, you find any one, you find delta E, you will get some answer, put minus for that, that is your delta E, or if you want work done, find delta E, put minus for that, that is the work done, because Q becomes 0. Okay, next the process is sixth process is polytropic process. So, this law is governed by the general law P V to the power of n is equal to constant. This power is for only V. So, this n is called polytropic index. P V to the power n is equal to constant. So, observe here PV diagram and TS diagram. So, we have considered 1 kg of wet steam being heated polytropically from initial state 1 to final state 2 in PV and TS diagram. The concentrations are similar to previous cases, that is P1 initial pressure, Vg1 initial specific volume, x1 initial dryness fraction. Similarly, P2 final pressure of steam, Vg2 final specific volume of steam, and x2 is final dryness fraction.